When last we left off, we were talking about fusion in the core. That is by far the hottest, densest part of the sun, and it's the only part of the sun where fusion takes place. This section talks about how does that energy make its way to the surface of the sun. There are two major regions it goes through, and this is a very simplified version of all this, but you have the radiative zone here and the convection zone beyond that. You'll also notice this straight arrow representing the path of neutrinos. We'll get to those momentarily. First up, though, where does this energy go? Well, it doesn't go far, because as soon as it's created in the core, it hits the worst traffic jam imaginable. The energy has to basically be absorbed by one atom and then re-emitted and then absorbed by another atom, and it makes its way atom by atom towards the surface in an incredibly slow process. It's called the random walk. As a matter of fact, the only thing that can go through this traffic jam are neutrinos that we mentioned, are these sort of ghost-like particles that have almost no mass, but they do have some mass. They go right on through the traffic jam and they get to Earth 8 minutes later after they're formed. It's going to take this energy in the form of photons a little bit longer, as in like 1,000,000 years. Yeah, it takes that long to actually bubble its way to the surface, astronomers think. It's just incredible. So I just want you to think of that. Next time sunlight is hitting your skin, just think about that. That energy was actually created 1,000,000 years ago in the core of the sun. And then it took an 8-minute trip to land on your skin. And at that point, the reason it's free to go, when it gets to the surface, basically there's nothing left to stop it. The traffic jam's over. It's not dense enough. There are no atoms to stop it, and you're free to go. It's like that amazing moment when the traffic magically clears and you're just free to take off. That's what happens, and it goes in the form of radiation. So there's radiation from the core through the radiative zone, and then the bubbling up process through the convection zone or convective zone, and then it becomes radiation again as it's free to fly through space and get to the Earth. Okay? So it's radiation briefly, then convection for a long time, and then radiation again, except for the neutrinos, which go right on through. See that little squiggle line there in white? That represents that random walk as the energy sort of makes its way out. That's kind of cool. That's a video I mentioned from the Stereo spacecraft, where there's one on each side of the Earth orbiting the sun, and they can take 3D images if you happen to have 3D glasses to check that out. All right. The so-called surface of the sun is where that energy is free to fly. It doesn't mean you can stand on the surface. We can't land anything on this surface. But we call it the photosphere because that's where photons can leave the sun. That's the part that you see with your eyes. When you see the sun with your eyes, you're seeing the photosphere. At that point, not only is the sun so much less dense than the core, it's actually less dense than air at that point. You are literally on the edge of space at that point, and that's why the energy is free to escape. The light can escape. And at that point, the temperature, remember, has dropped from 15 million Kelvin in the core to a mere 5,800 Kelvin, or maybe 10 to 12,000 degrees Fahrenheit. So there are some of the different zones we talked about. The sun is incredibly complex. This is a very simplified version. But anyway, let's talk about that surface a little more. When you take a close look at the surface, especially with the right kind of filter, like a hydrogen alpha filter, you see granules. These granules are little, I call them little plasma fountains that bubble up, and they look so tiny, but it's only because the sun is so huge. They're actually the size of like North America when you see these little bubbles coming up. And that's really what they remind me of, like watching a water boiling in a pot and the bubbles are constantly replaced by other bubbles. That's what this is like. And literally from the Doppler shift, blue shift towards us, red shift away from us, we can tell that what's happening is the energy is going up and then curling down the sides of each of these little plasma fountains that we call granules. Let's just watch. This is something you kind of have to see. It's a lot easier to see than to explain in words. So there it is. This is a time lapse over about 20 minutes where you can see, you can see the bubbles there. Again, each one of them the size of North America, each one of those little granules. Amazing, kind of mesmerizing to see the surface of the sun in action. All right. Now, the other thing the surface of the sun is known for are these dark splotches, that what Galileo saw all the way back in 1610. And those splotches, of course, are called sunspots. They also look pretty small. They're larger than granules. They still look pretty small, and yet they are the size of planet Earth. So keep that in mind. If you get a chance, we have a solar filter at our school. We're able to look at sunspots and take pictures of sunspots, and they always look so tiny. And I have to remind the kids that you're looking at something the size of Earth. Sometimes there are a lot, sometimes there are none. And some years are better than others, as you're going to see in a minute, because it goes through a cycle. Sunspots can last a wide range of times. Some of them can last long enough so that they come back around as the sun spins around. Sunspots, why do they appear dark? Because they are relatively cool. So if they're 9,000 degrees and the surface around them is 11,000 degrees, relatively speaking, they are cool and they appear dark. If you could magically pull a sunspot off of the sun, it would be super bright. That's what's really neat about this. It's like an optical illusion that they appear dark because they are actually super hot, just relatively cool. They're actually the coolest spot on the sun, we say, the coolest part of the entire sun. The temperature drops from the core all the way to the surface, and then on the surface, they are the coolest part. Now, they also have two areas. A sunspot has two basic areas, a penumbra and an umbra. Yes, you've heard these terms before. They're used with eclipses. So if you're in the darkest part of the shadow, remember you're in the umbra. You're in a total eclipse. And then the penumbra is a partial eclipse. Well, here, you see that little area there? That's sort of the suburb, I like to say, and that's the penumbra. And then, of course, the really dark area, the downtown, that's the umbra for sunspots. You'll also notice there's kind of almost like two downtowns there, and there's a good reason for that we'll get to in a moment. We mentioned already sunspots rotate fastest at the equator. And as I also mentioned, we're able to take some pictures. So here's a year in 2012 where we weren't seeing too many sunspots, just a couple here and there. We also started getting better. And so by the class of 14, look at this, we started seeing that the sun was more active, and we were actually getting better at photographing them and stuff like that. And you can see a lot of sunspots. We also have a hydrogen alpha filter. It's not that great, but we can also sometimes see little flares and things like that. Looks like that's the class of 14 as well. Okay, so why were there two sort of downtowns? That's because sunspots are caused by magnetism. And what's the number one thing you learn about magnets? They have a north and they have a south. So sunspots have a north end and a south end. They come in pairs. The south, by definition, just by definition, is where the lines are coming up out of the sun. And by definition, when the lines go back into the sun, we call it the north. They don't have to be turned north and south. Those are just the terms we use because we're used to using those terms for magnets anyway. This gets really interesting. It's kind of strange. But the sunspots are always oriented the same way within a hemisphere. So within the entire northern hemisphere, they're all turned one way, north, south, north, south. And within the southern hemisphere, they're actually turned the opposite way, as you'll see. Let's take a look. So here, with what's called I think a magnetogram on the right, they've done it in white and black. So you've got white, black, white, black, white, black there in the north. Now, what happens here, look at this. And this is just the strangest thing ever. But after a complete solar cycle, they flip. The poles, they actually flip their direction, which is just a really crazy, amazing thing. So what happens is, look at this. In cycle 21, you had, I don't know which one's which here. Let's just say the blue is north and the yellow is south. So look at this. In the northern CEQ for equator, blue, yellow, blue, yellow, blue, yellow. So north, south. You go to the southern hemisphere, yellow, blue, yellow, blue, yellow, blue. So the north and south are always oppositely oriented. But then after this 11-year cycle, which is just insane, after 11 years, suddenly they flip. And you'll notice here in cycle 22, it was all yellow, blue in the north and blue, yellow in the south. it's just crazy stuff. So, I mentioned that 11-year cycle. Look at the difference in activity between a low part of the cycle and an active part of the cycle. And I can tell you from firsthand experience in our class, it's just a huge difference. So we had some years, I want to say back in around 2010 or so. I mean, we had no activity on the sun for years. I mean, for 2 or 3 years, it was in a real lull and we weren't seeing any sunspots and stuff like that. And then it really picks up in the solar cycle. Look at that. You can have a whole lot of activity. So as mentioned, it's every 11 years. That's the key. And that's when it becomes dangerous because the sun is going to become very active every 11 years. There are more solar flares and potential hazards for things like satellites as the sun sends bursts of energy and particles towards the Earth. That can cause a real problem, as we'll talk about later. So technically it's a 22-year cycle because it's 11 years and then the poles flip and it's another 11 years. I think the 11-year cycle is more important to think of because that's when it peaks in activity and that's when it becomes sort of dangerous. All right. There was one time when this 11-year cycle was broken, which is quite the mystery still to this day. It's called the Maunder Minimum. Look at that. In the mid to late 1600s, early 1700s, the sun just took a break. There were almost no sunspots, and they could notice the difference. There were no northern lights and things like that. We still don't know why it did that for those decades, but it did. And what is probably not a coincidence, it got really cold for a prolonged period of time. They sometimes call it the Little Ice Age. There's the famous picture of Washington crossing the Delaware and his men pushing back chunks of ice. Well, guess what? The Delaware River would never, ever freeze in modern times. It doesn't freeze anymore. Here's a town in Holland where it shows them out in the 1600s playing on the ice. That lake never freezes today. So we have a lot of circumstantial evidence for how cold it was during the Little Ice Age. And it was really a bad thing. I mean, it caused famines in different places and stuff like that as well. Here's another picture showing the difference in activity. Near the sunspots, you tend to have these big loops, which are called prominences, and you can literally see the plasma go up one side of the arch and down the other, which is also, of course, caused by magnetism. If you look straight down on a prominence, it's called a filament. It just looks like a straight line. And these prominences can be pretty huge. Okay, you could think of them like playing croquet. You could hit planets through these things. They're so huge. So these are actually loops here, but when you can't see it, it's like flying over the arch in St. Louis. If you're looking straight down on it, it just looks like a line, and that's what's happening here. So those are actual loops called prominences, but when you see them from that angle, they're called filaments, and just amazing stuff. Let me show you, I think on here is the largest prominence I've ever seen. Here's just one taking place. Watch this, where the plasma loops up and around those magnetic field lines from the south to the north there. Really interesting stuff that takes place all the time. This is the largest one I've ever seen. This is a really old picture. Look at that monster. I mean, you could actually you could throw Jupiter through that prominence. Not just the Earth. You could throw the planet Jupiter through there. Through that loop. Pretty amazing stuff. Let me see if this video is going to work here. Now, this is forming something even more really than a prominence. When it starts to look like a big slinky, I like to call it a solar slinky, that's called a flux rope. A flux rope. Look at that. Just crazy. That's our sun. Amazing stuff. Absolutely amazing. That's from that SDO, Solar Dynamics Observatory, which is at the L1 Lagrange point between the Earth and the Sun, taking amazing pictures of the Sun all the time. More energy than a prominence, a loop, is when the plasma goes up and it doesn't return. That's called a flare. So just like escape velocity takes more energy than orbital velocity, in this case, instead of looping back down, the material is shot out into space, and of course it can head towards the Earth, which is dangerous. And the biggest types of flares are called coronal mass ejections. There was one very famously in 1989 that hit the Earth and actually wiped out the power grid of Quebec, Canada. Let's watch. Look on the right. Look at that. That's actual material. That's the dangerous part, traveling at tremendous speeds, and takes maybe a few days to hit the Earth. And anyway, we're about out of time. We're going to watch just a little bit of this and let it play out. Thanks for listening.